This is Ravi Kumar. Welcome to my channel Future Tech Research Institute, FTRI. So in this lecture I would like to explain the MOSFET I-V relationships. MOSFET, metal oxide semiconductor field effect transistor, and the cross-section diagram of MOSFET, it looks like this. I have taken NMOS transistor, N plus source, N plus drain, and P-type substrate, and gate is there. Okay, so this is a blank transistor without application of any voltages. So let us see when we apply voltages to that and what is the relation between voltage and current equations. That I would like to derive here so compactly and so easily that you can follow me. Okay. Well, I have taken NMOS transistor. Here source has to be grounded and bottom body is grounded here, and gate should be applied to positive voltage to make it on, and drain also should be applied with a positive voltage to collect some drain current. So here, so if you apply a very low positive voltage to the drain, and as you keep on increasing gate voltage to the positive side, what will happen? When you apply the gate is a metal here or a polycrystalline silicon, and then we have an insulator, oxide, silicon dioxide is insulated there, and below semiconductor. This is a P-type semiconductor. So N plus source and N plus drain. Okay, so MOS, metal oxide semiconductor. So oxide is acting as a dielectric here. So due to dielectric polarization, we can see that the negative charges are there at the the top of the dielectric layer, and the bottom of it, the positive, it will be positively charged due to the polarization. So that will attract due to this positive charge. So that will induce, the background is also P-type there. P-type means in the P-type semiconductor we have all holes, positively charged particles. Okay, so they will be depleted, okay, because there is a positive charge in the dielectric that will be repelling the positive mobile carriers here. So this is not mobile actually, they are actually the polarization. And in the metal we have the mobile carriers. So in the dielectric the carriers are not mobile, but it is only polarized. The negative charge is going to the top and positive charge is going to the bottom of the dielectric layer. So that positive charge is at the bottom of the dielectric layer is repelling the mobile positive carriers in the silicon there, the background silicon, that is a body. So that means the holes are getting repelled, that is going down, they are called the depleted. Okay, so they are getting depleted. When the holes are leaving the atoms there, what will be left behind? We are left behind with negative immobile ionic charges. So that is a depletion charge. So negative charge is there in the P-type semiconductor. Similarly, we can see in the source and drain also. The source and drain, there is a source to body junction is there, NP junction, PN junction, and drain to body PN junction. So body is ground here and source is ground. Even though both are there ground, so there will be a built-in potential. Okay, so that there will be a positive charge in the P-type semiconductor. The negative charge in the P-type semiconductor. So that will be immobile ionic charge, and positive charge in the N-type source. Similarly in the drain side. So here at the top there is no junction there. This is a MOS capacitor. It is acting as a capacitor, and the positive charge which is there in the dielectric is being balanced with the immobile ionic charge. So as you keep on increasing the gate voltage, what will happen is the mobile charge will be keep on depleting, and the surface potential will be slightly lowering down. So there is a built-in potential between N plus source and P-type body there. So this built-in potential will be lowered, keep on lowering at the surface here due to the applied voltage at the gate. The surface potential will be keep on decreasing. So at a point of time, the surface potential will be so decreased that the electrons will be flowing from source to the body. So they will be contributing to mobile electron charge. Mobile electron charge. So now there won't be any further depletion of the holes from the background P-type semiconductor, but the positive charge, when you increase the gate voltage, what is happening? You are increasing the positive charge in the gate, and thereby increasing the positive charge in the dielectric also, and that has to be compensated, that has to be balanced with the negative charge in the background. So the negative charge which is balancing the positive charge in the dielectric will now be collected from the source. They are the mobile electron charges, electron carriers. So this is called a channel here. Okay. So these mobile carriers are acting as the channel which is used for conductor, through that channel there will be a current flowing from source to drain. So it is acting as channel actually. Okay. So now the current which is flowing from source to drain, how much current will be flowing, that depends upon the total charge which will be there in the channel and how much voltage that you are applying across drain to source. Okay, so you can look at it as a simple resistor, and the resistivity of this channel will be reduced when you increase the number of mobile carriers here, and the current will increase when you increase the voltage across the resistor, obviously. Okay, what is, you can just look at a simple resistor, the current through a simple resistor, and you're applying, this is ground, and you're applying some voltage, positive voltage here. What is current? V by R. Okay, so the resistance of the channel is decreasing as you increase the gate voltage, slowly decreasing. That will cause the current to increase. Okay, and what is the implication of voltage here? This voltage is the drain to source voltage, the voltage across the resistor. VDS is acting as voltage across the channel. That is a resistor. Okay, so when you increase the voltage across the channel, that will also increase the current. When you increase the gate voltage, that will decrease the resistance of the channel. So thereby increasing the current. So that this is a qualitative analysis. Let us say the quantitative. We can quantify it. What will happen when you increase the voltage further? Okay, when you increase the gate voltage, what is happening? As I said, you are increasing the charge carriers, the mobile electron charges in the channel. They'll keep on increasing. Okay, so we can see here for sufficiently very low, or very, suppose you not applied any drain voltage, this also if you can ground, there is no current flowing right now across the MOS transistor. There is no current flowing through source to drain. Okay, when drain is also ground. So what is happening is you are simply increasing the charge density, the mobile electron density in the channel. Keep on increasing as you increase the gate voltage. Okay. Now for a particular gate voltage, when you fix the gate voltage to some high positive voltage, now as one more point here, as you keep on increasing gate voltage, as I said, the surface potential will be keep on reducing. Okay, so and we can see that the background type semiconductor is p-type semiconductor, so that will have a potential, surface potential, the potential of the p-type semiconductor. When the carriers are increasing, gone to the strong inversion, and the minimum gate voltage that is required to make the surface potential twice that of the background potential, that gate voltage is called threshold voltage. Okay, threshold voltage is nothing but the gate voltage, gate to source voltage, which is required to make the surface potential twice that of background potential. Okay, so after that, whatever that voltage that you are applying, what will happen? That will further increase the charge carriers anyway. Okay, now 3 volts. What will happen? Drain side it is 3 volt, source side it is 0 only. There is a connection between source to drain through the mobile carrier charge there. Okay, now so this channel, the voltage along this channel will be varying from 0 to 3. At this side it is 3 volt, at the source side it is 0 volts. Okay, now similarly, and the voltage across drain to body junction is more here, 3 volts, and source to body is only 0. So the thickness, the depletion layer thickness also will be changing. It will be more in the drain side. Okay, so depletion region, which is consisting of negative immobile ionic charge, will be increasing in the drain side. Similarly, to balance that, it will be increasing in the N plus drain also, positive charge. Since it is highly concentration, the thickness will be less, of course. Okay, so what is happening to the channel mobile electron charge here? So will it be same along the channel? It won't be. Why? Because here the channel voltage, the voltage which is supporting the channel here will be more at the source side. VGS minus VT minus Vx. Vx is the voltage at a particular location along the channel. Okay, so as I said, VDS is changing from source to drain, so I'm calling it as Vx. So Vx is a variable voltage along the channel. So for example, at the source end it is 0. So what is the voltage across the channel which is supporting that? That is given as channel supporting voltage. So channel support voltage is VGS minus VT minus Vx. So this is called the channel support voltage. So for certain values here, if VGS equal to 2 volts and VT is 2 volts, 1 volt, and Vx at source side it is 0, so then VGS minus VT minus Vx will be 2 minus 1 minus 0, that is 1 volt here. So 1 volt is supporting. So at some other point, say for example, take the 2 points, one here, another point here. At that point, say it is say 1 volt. 2 minus 1 minus 1, it will be 0 volts. So it will be means the channel support voltage is becoming 0 at a particular point where Vx is 1 volt. So that means the mobile electron charge will become negligible at that point, and later on there won't be any mobile channel there, but they will be swept to the drain with the highest drift saturation velocity. Alright, so we'll come to that. So the channel thickness is varying along the channel here. So the channel support voltage is different at different locations along the channel. Okay, so that's the thing. Now let us see. This is called the channel support voltage, VGS minus VT minus Vx. Okay, so now to derive the expression for the current, source to drain current, IDS, current flowing from source to drain for a given VGS. So we'll derive it by taking an elemental channel of thickness dl. So let me magnify it. Let me magnify this elemental channel. It will be like this. This is a gate, and below we have the elemental channel. So along the elemental channel we can assume that the thickness is same. So this is consisting of electrons. So we are having the positive charge here and the negative charge here to support, like this. So this is elemental channel, length of dl, say. Okay, so now to derive the equation, the current equation, current is nothing but rate of flow of charge, is nothing but the electric current, charge per unit time, dq by dt. So dq is the elemental total charge in this elemental channel, dq. And for example, if the elemental charge takes time of dt seconds to cross this length dl, so we can say that the current is dq by dt. Current is dq by dt. Okay, now so now we have to get the expressions for dq, the elemental charge, the total charge in this elemental channel. Alright, so now here we see that whatever voltage that you are applying across the gate to source, so that is acting, that is giving the vertical electric field, that is only used for supporting the channel. Okay, further increase in the gate voltage will increase the concentration of mobile charge carriers in the channel. But the voltage across drain to source, so that is applying a lateral electric field across drain to source, that is causing the flow of charge from source to drain. They will be flowing from source to drain. There is a lateral current. So though there is a vertical field, the charge carriers cannot flow from channel to gate because there is a dielectric here. Insulator is there. Metal oxide semiconductor. Metal insulator semiconductor. So current flow is not there in the vertical direction. Current is only in the horizontal direction. Okay. So gate voltage is responsible for holding the channel, and drain to source voltage is responsible for collecting the charge carriers. So let us see the expressions for dq here. So dq can be obtained as the charge is given by capacitance into voltage, Q equal to CV. The capacitance of this elemental channel can be obtained as, you can see as a gate width is W, as I said, width is W and length is here DL only. So there is a dielectric layer here in between. So the capacitance per unit area of this capacitor, there are two plates, top is gate, bottom is substrate. So between these two plates, the capacitance per unit area is given by the permittivity of the oxide layer, the dielectric layer, divided by the thickness of the oxide layer. This is Tox, oxide thickness. So epsilon oxide by Tox. So that is the capacitance per unit area given by farad per centimeter square. Now to get the capacitance of this elemental block, so we have to multiply that with the area of this gate. Okay, so Cox into dq will be given by Cox into the area of this, W into dl. So that is the total capacitance in farads only. This is farad per centimeter square multiplied by the area, that gives farads. This into C into V, the voltage across this. What is the voltage across the gate to channel? As I said, the channel support voltage, that is VGS minus VT minus Vx. Vx is the voltage at that particular location. VGS minus VT minus Vx. So this is dq here. Okay. Now what is the current? Current is given by dq by dt. That is equal to Cox into W into dl by dt here into VGS minus VT minus Vx. Alright. Now I have taken just an elemental channel here. Okay, so the current is flowing from source to drain, from left to right, along the channel. So we can see this channel as divided into different blocks, small elements. We can see them as different resistors connected in series. The current which is flowing through one elemental block should be same as the current flowing through the other blocks, and the total current is same because it is connected only one path. Okay, so the resistance may be different, the resistance of different blocks may be different, but the current through the channel is same, should be same. The total current is equal to the current through any elemental block. So that is the thing here. The total current I is equal to dq by dt here. Okay, so now we have to convert this dl and the dt's into, we have to integrate this to get that total current actually. Okay, now let me introduce another parameters here. So now since you are applying a horizontal field, the electrons are drifted from source to drain. There are two phenomena here. The current is due to drift and diffusion. The drift is due to the electric field and diffusion is due to the gradient in concentration. So the current, the mobile carriers will also be moving from one location to the other when there is a gradient of concentration, from high concentration to the lower concentration. But here the drift is dominant here. When the electric field is significant, the drift current is dominant. So we are considering the drift current here. So due to that horizontal electric field. Here we will introduce a parameter. What is the electric field here? The horizontal electric field. The voltage across this elemental channel, let us say dVx. The electric field is given as, the electric field, I'll call it as, I'll introduce some other physics here. The electric field is given as, along the elemental channel is given as dVx upon dl. And there is one more physical parameter which is called the drift mobility of the charge carriers, which is denoted as mu. And drift mobility, velocity of the carriers per unit electric field. The velocity of the carriers will increase as you keep on increasing the electric field. Okay, the proportionality of this, the velocity is proportional to the electric field, and the proportionality constant is here is called the mobility here. So mobility, you can say that velocity per unit electric field. So velocity of the carriers, I call it as u, here U by Ex is your mobility. Okay, this is called the mobility. Mobility of mobile charge carriers. Here it is electrons. U is the velocity, drift velocity. Okay, so here dl by dt can be treated as the velocity of the carriers. Okay, as I said, the current through this is given by dq by dt. dt is the time taken to cross from left side to the right side of this elemental block, and the dl is the length. So dl by dt is the drift velocity of the carriers there. So dl by dt we can replace that, so we can replace dl by dt with u here. So u is nothing but, this implies u equal to mu into Ex. Mu n is mobility of electrons here. So what is Ex here? Ex is dVx by dl. dVx by dl. So this is equal to mu n into dVx upon dl. Okay, now I will replace dl by dt, which is nothing but u. So u equal to dl by dt equal to mu into dVx by dl. So this will be replaced here. I am replacing dl by dt with these terms, mu n into dVx by dl. So dq by, the current through the elemental channel can be obtained by dq by dt, and after replacing dl by dt with this mu into dVx by dl, the equation is Cox into W into mu Vgs minus Vt minus Vx into dVx by dl. Okay, so integrating this from source to drain, L is from 0 to L, and VDS is from Vx is from 0 to VDS. Okay, now, so even when you integrate, the current should remain same. Okay, so the I equal to IDS equal to integrate from 0 to VDS and integrate from 0 to L dq by dt, that is equal to integrate from 0 to VDS, that is Vx is there, in this term only, Vgs minus Vt minus Vx into dVx into Cox mu into W and by dl. Okay, so integral 0 to L. So that is equal to, when you integrate from 0 to L with respect to dl, so that becomes L only. So that becomes, divided by L. So we can take it out. Let me rearrange. Mu into Cox into W, there is constant. When you integrate with respect to L, that becomes L here, and integrate 0 to VDS. Next term is this, Vgs minus Vt minus Vx dVx. Okay, so there are two terms in this, Vgs minus Vt and minus Vx. Okay, when you integrate that, mu Cox into W by L, then you integrate with respect to Vx, this becomes Vgs minus Vt into Vx, one term, minus Vx dVx, so that becomes Vx square upon 2. Limits are 0 to VDS. Okay, so after substituting the limits, let me rub off this, the top two lines. So now we can get the current IDS equal to, after substituting the limits, mu Cox, I replaced mu n with mu, it's a general term. For NMOS it is mobility mu n, for PMOS it is mu p. Okay, mu Cox W upon L, Vgs minus Vt into VDS minus, when you replace with VDS here, VDS square upon 2. For the lower limit, when you replace Vx with 0, the term becomes 0, minus 0. Okay, I am not writing that. So this is the current equation. This is a drain to source current equation. Now, there are three cases when VDS, drain to source voltage, is less than Vg minus Vt. Then we can say VDS is very less. That time we can neglect this term. When VDS is less, much less, we can neglect this term. It is VDS square upon 2. This becomes negligible. So we can write that case 1, when VDS is less than VGS minus VT. So we can neglect this term. So IDS becomes mu Cox W upon L VGS minus VT into VDS. Okay, so we can see from this equation, for a given VGS, gate to source voltage, these are constants. For a given geometry, W and L is fixed, Cox is fixed, mobility is constant, and VGS given for a particular voltage, and VT is constant. And current is linearly varying with drain voltage. This is a linear region. So in the linear region, it's a resistive region. Okay, so this is the first equation. This is called linear region. Now the second case when VGS is comparable with VGS minus VT, near to that. So then what happens is comparable to that, much less than VGS minus VT, then it is linear. When it is comparable to that, then both terms will be coming into picture. So it is deviating from linearity. There is a minus term VDS square upon 2, so it will deviate. So this is a non-linear region. This is non-linear region. So the first equation here itself is the second case, that is non-linear region. So the third case is when VDS, drain to source voltage, is greater than VGS minus VT. What will happen? What will happen when VGS is increasing further, more than VGS minus VT? So as I told you in the beginning, when you keep on increasing drain to source voltage along the channel, a position comes where the channel support voltage, that is Vg minus Vt minus Vx, becomes 0. Okay, now, so when that becomes 0, that is called the pinch-off voltage. Okay, so when you keep on increasing drain to source voltage, that will not increase the voltage across the channel. The Vg minus Vt minus Vx is fixed. It is already pinched off. So further increase in drain to source voltage will not increase the voltage across the channel, the internal voltage across the channel. So that is deciding the current. So as soon as the carriers reach that pinch off region, they will be drifted to the drain side by high electric field, high velocity. So now the current, the drain to source current, is not limited by how fast they are collected across this region, but how fast they are supplied by the channel. So the supply of the carriers by the channel to the pinch off point is limited by the voltage across it, that is VGS minus VT minus Vx. So current will not further increase, it will be saturated. So at VGS minus VT, the voltage across this becomes constant, and across the channel becomes constant, and the current becomes saturated. So the equation will become VDS will be equal to VGS minus VT. It will not increase further. Okay. So the current will be equal to mu Cox W by L VGS minus VT into VDS is now replaced with VGS minus VT minus VGS minus VT whole square upon 2. Okay, so now the VG minus VT into VGS minus VT whole square minus VGS minus VT whole square upon 2. So this will be mu Cox into W upon L into VGS minus VT whole square upon 2. So now this is the expression for drain current, drain to source current in the saturation region, for which VDS is greater than or equal to VGS minus VT. This is called saturation. That means there is no VDS term in this. There is no VDS term in this. The current is saturated. So further increase in VDS is not changing the current, ideally, for a long channel device. Of course, for any other short channel devices, there are second order terms will come into picture, second order phenomena, which is called channel length modulation and drain induced barrier lowering, and threshold voltage itself will decrease, and velocity saturation will be introduced. So many second order phenomena will be come into picture. So there you can see that the current also will change in the saturation region slightly, because this VT is again depending upon VDS, and mobility length is also depending upon VDS and all. Those are the second order terms. But for this long channel approximation, the current should ideally saturated. After VGS minus VT, the current will not be depending upon VDS. There are three regions: linear region, non-linear region, saturation region. So we can see this graphically with simple analysis. So there are three equations. Let me draw the graph for this. The current voltage graph in all the three regions. VDS versus IDS. So first I said, as VDS is increasing in when it is very low, the relation is linear, resistive. As increase further, it will deviate from linearity, and then at a point it becomes saturated. It won't change with VDS. Okay, so now we can see some regions here. So we cannot bifurcate very precisely the deviation between from linear to non-linear, but we can see some point here. This is linear, non-linear, this is saturation. Okay, so now what will happen if you increase the VDS further, keep on increasing? The current, something else will happen. Further increase in VDS means source and body is also grounded. So the voltage across this PN junction, drain to substrate junction, will keep on increasing. So a time comes when that will introduce the electric field across the junction will be high enough to introduce impact ionization. So it will cause some junction breakdown, and the current will increase, shoot suddenly, So that's called the breakdown. It's not permanent breakdown of the device, but it will increase the current all of a sudden. Okay, so that is called the breakdown region. So it will increase when you keep on increasing the current voltage across it. So that is the breakdown region. So these are four regions of operation. So I have derived the expression for drain to source current for different regions: linear, non-linear, and saturation region. And I have given qualitative and quantitative analysis. See you. Don't forget to like this video and subscribe, and put your comments and ask any doubt if you have. I'll be checking my the comments once in a while, and I'll try to answer your comments, your questions. And visit then FTRI and subscribe to this channel, Future Tech Research Institute channel. Bye. See ya.